It highlights promising results using the Neurovista dataset, achieving predictions better than random and comparable to state-of-the-art models.
Yeah, so we'll see about that. I don't think they actually did a comparison to other models.
Limited dataset generalizability. Reliance on the Neurovista dataset limits applicability to other datasets, especially scalp EEG or different electrode configurations.
Yeah, so one of the obvious things that stand out is, yeah, it seems like they only used one dataset and potentially also use one way of processing. So LSTM model was the only one used in this study. There is supposedly, allegedly, no explanation of what the LSTM model actually learned. So there's supposedly no in-depth discussion of what features were actually used to make the predictions.
The paper relies exclusively on the Neurovista dataset, which is widely used in seizure prediction research, but has inherent limitations. This dataset consists of long-term intracranial EEG recordings from a small group of 15 patients with focal epilepsy, which limits its representativeness of broader populations. For example, it does not include data from scalp EEG, different electrode configurations, or patients with generalized epilepsy.
Yeah, it's always suspicious when you see a patient 1 to 15, but then it goes 1 to 3, 6, 8, 9, 10, 11, 13, 15. So yeah, 5 of them are missing. Supposedly there was insufficient seizure count, but then, if you're using a model, I'm wondering why not just leave the data there. Well, I guess the rationale is that the different performance of different patients in terms of, so there's essentially different predictability level for different patients.
The model's performance varies significantly across patients, highlighting a key limitation in its ability to generalize effectively. While some patients, like patient 1 and patient 11, achieve high AUCs and sensitivity, others, such as patient 6 and patient 15, perform poorly, with low sensitivity and predictive accuracy.
So ideally we would like, so either fine-tuning something for a specific patient, which is possible considering, these patients had an implant. There's not many of them, so you might as well fine-tune a model for a specific patient. I don't think it sounds too far-fetched. Again, considering there's only 15 of them, not too many events, at least for some of the patients that were even excluded from the data analysis. And then they also have an implant, so the recordings are long-term. So it's definitely worthwhile doing machine learning and feeding, the results back into the model to try and improve it. And yes, eventually fine-tune and optimize for a patient-by-patient basis.
The model often produces a high start time in high, which represents the proportion of time the model predicts a pre-ictal state. While higher sensitivity is achieved in some cases, this comes at the cost of frequent false positives.
Yeah, I'll quickly go over the comparison between a paradigm 1 and 2.
Paradigm 1 versus Paradigm 2, key differences and observations. Labeling scheme. Paradigm 1, preictal data is labeled as 1 to 16 minutes before a seizure, and interictal data as more than 16 minutes before a seizure. Paradigm 2, preictal data is labeled as 1 to 4 minutes before a seizure, and interictal data as more than 4 minutes before a seizure. Performance comparison. Paradigm 1 generally shows better AUC values for patients who benefit from longer preictal windows. E.g., patient 1 achieves 0.86 in Paradigm 1 versus 0.74 in Paradigm 2. Paradigm 2 performs better for patients who exhibit stronger predictive features closer to seizure onset. E.g., patient 6 improves from 0.63 in Paradigm 1 to 0.77 in Paradigm 2. Statistical significance. Patients like patient 1 and patient 13 show significant differences in performance between paradigms, as indicated by non-overlapping confidence intervals. For other patients, such as patient 2 and patient 9, the AUC values remain consistent between paradigms, suggesting robustness across different labeling schemes.
Well, right. So there's definitely a need for personalized approaches. I think that's the the biggest result of this study. However, so they have these two paradigms, right? So taking a different window size before the seizure actually occurred. So preictal is before you have epileptic activity in the EEG starts happening. So in this case, if we're going 16 minutes before a seizure, well, then we would definitely expect in the paper, once we train the model or the authors should have then, we expect for them to explain to us what is it in the signal that we start seeing a whopping 16 minutes before a seizure event. What is it in the signal that the model, currently this LSTM model, is actually detecting? What feature in this waveform is actually changing that we can essentially predict a seizure a whopping 16 minutes before it actually occurs? And yeah, we will see if it's actually is presented in the results of this paper. Spoiler alert, I don't think it is. Well, yeah, that's actually the main point, is yes, that once you make the model essentially better, you increase its sensitivity, well, then you increase your false alarms as well. So that's all you need to know. It would be interesting to know if this was actually addressed in the paper. LSTMs can classify and process EEG recordings. Okay, of course they can. You can, use essentially any algorithm on it. Question, is it useful? And it makes seizure predictions better than chance. Okay, better than chance. We can do better than chance.